This morning, we're going to have Brant Ross delivering our presentation. He has many years of experience in multi-body dynamics. He has been an owner, founder, president of MotionPort. We are pleased to have him as the CTO currently at EngineSoft USA. And he is going to go ahead and present about precise robot and robust robots developed through high-fidelity multiphysics simulation. So with that, Brant, I will turn it over to you and you can get the ball going.
Okay, very good. Thanks, Alana. Yeah, so today we'll talk about robot development, and I think we'll see some interesting examples of robots that have been simulated. And then for three of the robots, we'll actually get into a case study for each one and go into a little bit more detail about some of the work that has been done. So, a robot is a mechatronic system, and all mechatronic systems are a combination of a mechanical system and then also a controller. And so with simulation, then it's very important to think about how to represent the controller as well as the mechanical system. And actually, to get very accurate results, then what you need to do is to have, as shown here in the second point, accurate representation of both the control system and the robot mechanical model. And so, in the case of the control system, to look at all the details of the logic and the inputs and the feedback. The mechanical system, a big help there is to add sophistication with regards to flexibility of components, possibly flexibility of connections, and then just to include any other physics that's involved in the model. If the model is interacting with the fluid or something like that, then that should be included in the mechanical model. So let's just dive in to look at some of the examples. So this is a pick and place robot that has a parallel linkage, as can be seen. So such a robot can be used, a robot model with simulation can be used to come up with what is the required size of the electric motors that might be used to actuate the different degrees of freedom of the robot. To be able to understand the functionality of the robot, then as we see here, the interaction between the suction and the balls, that involves some contact modeling as well as having the right attraction force, also contact modeling between the balls and the holes and so forth. Here's a very precise robot. It's a Scara Robot, selective compliance articulated robot arm. So it has compliance in the X and Y axes, but rigid in the Z axis. And so by simulating such a robot, one can carefully study the accuracy of the controller. And part of the function of the controller for basically any robot is not only moving the robot into the different positions of interest, but then the controller aspect of it is going to look at different information that's sensed, data from sensors, and also looking at the issues of bringing the robot into each new position in a way that is not going to have an excessive acceleration, to basically have smooth behavior of the robot, so that it can converge to its new position as fast as possible without vibration. And of course, to see some of these effects, that's where the compliance modeling comes into play. So we're gonna do a quick case study here, looking at a robot that's developed to do shopping, like grocery shopping. And I think we're all familiar that a few years ago during the COVID time period, there was a lot of online shopping, and that was motivated by people not wanting to be exposed to other people. And so then they would order their goods, and the goods would be picked up and then delivered. Or maybe the items would be picked up in the store and put together, and then the customer would come and pick it up at the store. So in looking at such a robot, really there were three factors that came into play to motivate its development. So we've already talked about the COVID time period, and then just the time to develop this online distribution industry, which included stores actually creating places for the items to be picked up, and then also to hire people to do this kind of work and to have a place for them to be able to select the items, maybe a separate warehouse. And then the third aspect of this was just for people to get used to this online customer consumer culture. And even today without COVID, the amount of activity that's going on with people ordering stuff and having it assembled in whatever way and then possibly delivered is much more prevalent than it was a few years ago. So often there's not enough people to take care of tasks when you have a large customer base. And so then the need here was to have a robot for shopping purposes. And so then we looked at using RecurDyn to do some simulation of the robot design, the shopping robot design, before building the physical prototype. So an important aspect of the robot, it's like, okay, we think about the robot and an arm that's moving around. But the gripper, when one is doing any kind of picking and placing, the gripper is just really essential. So in this case, this was a challenge then to have a robot with a gripper that could function for a wide variety of different packages. So in this case, gripper was designed, and it has the three different fingers, as we can see, and then those fingers could rotate and basically assume different configurations. And the different configurations were needed for the different packages. So with the case of the milk carton, half a liter, basically the gripper was set up so that two fingers would just squeeze together to grab the sides of that milk carton, and then the third finger just stayed out of the way. In case of picking up a tennis ball, some kind of a spherical surface, basically it was a three-finger mode, evenly spaced. And then in the case of grabbing a cylindrical type of configuration, then all three fingers are used, but two are on one side of the cylinder and one is on the other side. And so that would really help with the gripping capability, to have all three fingers engaged. So we can see the desired motion is depicted in the motion column on the left, and then on the right columns here are showing models in RecurDyn with this gripper and looking at the different configurations, looking at how much force, gripping force, could be applied to each object in order to grab the object and avoid any kind of slipping of that object. So then this shows the robot being tested, and it's grabbing the different types of objects and assuming the different configurations. And you can see it's going from table to table with the different goods on there. So, and this brings up the point that robots, besides having the robotic arm, many robots are independently driving around. And so then there's issues of, coming up with the rest of the system, to have the mobility platform to move the robot arm from place to place. And in this model, you can see how the shopping robot is crossing a bump as part of this general simulation. And so that's another part of the evaluation. So when you have a mobility platform and navigation, then to keep track of the position of the platform and to be able to recover from errors that are imposed by irregularities in the terrain, and any possible deviations, slipping of the wheels and so forth. That's important to have that and to understand that as part of evaluating the system. Another thing to check would be, is the mobility platform moving due to the motion of the arm, and how large the inertia is that might cause some kind of motion there. So one study that was done with the shopping robot was to look at the robot picking up the different objects from different offsets. So to look at these animations, it looks like basically the same thing is happening with all the different offsets. But of course, we would expect that the forces, the loads, and the joints are going to be different with the different offsets to the side. And so then, with the simulation capability, when one is looking at the dynamics of the arm motion, one can then take the torque information in each joint to drive the motion, and then combine that, take the product of that and the angular velocity in order to come up with, the amount of energy and power that's occurring, at a given moment in time, in order to evaluate the different concepts. And so as we look at the different joints, the robot arm is actually going through different configurations. So as we scan these different offset distances, we can see that in the 6 different joints, the joint that is using up the most power isn't always with the largest offset. Most of the time, the largest offset is requiring the most power, but not all the time. And that's because the robot is reaching in different ways, given the different offsets. And so therefore, a given joint might happen to follow a configuration such that it's not using as much power. But if we look at the total power being produced or being consumed there at the bottom of the table, then we can clearly see the trend and, basically the amount of power consumed at the smallest offset is significantly lower than at the larger offset. And then the plots are showing what that power consumption is for the different joints as a factor of time. So all these things can be studied in order to try to basically maximize the productivity of the robot. At this point, there's a couple questions that have come in, so let me tackle those at this moment. So the comment was that it's useful to use CAD data and data sheets to model the dynamics precisely. And I think the idea is keep the tolerances low. So yes, that's absolutely right. And so that's why it's important that the simulation package RecurDyn is able to import the CAD data directly and use that geometry for the dimensions, for the joint locations, but also the geometry can be used for modeling contacts where that might be occurring. So that keeps the precision there. And then for data sheets, data can be imported in the form of splines, nonlinear splines to represent certain relationships. And then data also can be referenced by the model in other ways as well. So that's important to be able to include all that information. And then there's a question about flex bodies and resolution for the flex body or for the joint modeling. So basically, we will be looking at examples with the flex bodies here a little bit later in the presentation. Rotational spring dampers can be applied at any joint where there's a rotational degree of freedom, and those springs can definitely be modeled using the nonlinear data splines. Then those spring dampers can have nonlinear spring stiffness and damping characteristics from those data splines. It's also possible to use a user subroutine to do things like hysteresis, and that's something we have done. And actually, I have a project coming up where I'll be doing some work with hysteresis. So that is also a capability of the platform. Okay, let me keep going here. So here's another robot model. This one is a platform that is serving to work with the movement of different objects from a given position to another position. And so we can see the platform on the top of the robot has capabilities for tilting and also rotating. And that's how it's able to grab a parcel, rotate it if needed, and then the tilting is used to distribute the product to the new location. So again, it's the mechanical model. We want to make sure that the loads are within what's tolerable for the material, and then also look at the different controller aspects. There is a mechanism for the robot, but there's also contacts between the top of the platform and the different objects being transported. So again, the importance of having the contact modeling. Here's the same robot, and here it's actually lifting up a shelf and moving it. So being able to look at, okay, what are the loads, throughout the linkage of the robot while these loads are being carried and so forth is important to look at. So this is a different type of robot. It's actually a tracked robot. It's used for urban reconnaissance. So if somebody wants to see what's happening, maybe in a hazardous environment or situation, they can send in this robot, and then the robot has cameras and sensors to try to provide data of what's happening, within a building or some other kind of urban characteristic. And so one of the mobility challenges is to be able to climb up a set of stairs, and this robot is able to do so. And actually the track assemblies at the front of the vehicle, you can see how they're pivoting up and down in order to either gain access to the stairs by being pivoted up. And then once the robot's going up the stairs, then the track assemblies are pivoted down to provide a longer effective wheelbase. to improve traction as the robot goes up the stairs. So that's one example of a tracked robot. A lot's being done these days with autonomous tracked vehicles for various applications. This is showing a complex terrain that was derived from map data. And so, with the off-road robotics and autonomous vehicles, then, having these terrain definitions is really important. And so, RecurDyn has the ability to pull in the terrain data from, a GIS system. And then in the RecurDyn model with the track assemblies are all the different, suspension, linkages, road wheels, track shoes. And so you might imagine there's many contacts going on in the track assemblies. And then, of course, the contact of the track links with the terrain. So just a lot of contacts. And then, we have the ability to do some basic soil modeling. So, the thing here is not only, well, in the case of surveillance, it's, the robot arm per se is not playing any kind of big role. Rather, it's all about mobility, being able to get to the right place, and then to check out the sensor capabilities, which are not only learning from the environment, but also being used for the autonomous navigation and so forth. So here's, this same vehicle as from the previous slide. And this is showing a basic operation of, basically trying to follow a prescribed path across the terrain. And in the lower left, we're looking at a control system. This one can be fairly simple in order to do the path following. It's quite straightforward. But, the steering, the one thing about tracked vehicles is that with a wheeled vehicle, you can separately control the steering angle, of the front wheels, and then that's separate from keeping the velocity at a certain speed, because the velocity control can be done, let's say, with the back wheels. In the case of a tracked vehicle, the two track assemblies are providing both the forward velocity and the steering. So then that gets a little bit more complicated to have both goals being reached at the same time. And so then now we add the complexity here of saying, okay, we have our tracked robot that needs to navigate, but we don't have a predefined path for every, well, we can have a predefined path, but the vehicle needs to be smart enough to be able to sense an obstacle and then have logic to be able to pass the obstacle and then continue towards the target path. So all the graphics in red here is representing the obstacle, and on the image to the left, it's showing the vehicle, and then this vehicle configuration is basically using 8 discrete sensors to be able to look at its environment in the forward direction and the side directions. So that's the setup of the robot. And then this is on the right showing the control system. And this looks like a huge number of blocks and paths and so forth on the controller, but actually, it's showing the separate logic for each of the 8 sensors. So once you have that set up for one sensor, then you just duplicate it for the other sensors. And this is being shown in a co-simulation with MATLAB Simulink. And you can see a block in the control system representing, the one that says RecurDyn and client 3.x. That's representing the mechanical system of the vehicle as part of the Simulink model. So that's showing the setup of all this, and then this is just showing the results. Really looking at different control approaches to the vehicle. So the green curve here is showing the use of RecurDyn with a product called pre-scan. So pre-scan has logic for obstacle avoidance. And then the red curve is showing using RecurDyn with our own controls package CoLink. And we can see that it was able to basically follow the same path as with the pre-scan software. And then the blue is just kind of showing the reference path of just following, a curve that's, that's predefined to avoid the obstacle. But the other two are automatically finding a path to avoid the obstacle. So the vehicle was running at 10 miles per hour for 30 seconds. The simulation of this took about 18 minutes to do. Then the chart on the lower part of the slide is just monitoring the forward velocity of the vehicle. So as the vehicle had to turn and so forth, then the velocity was going to slow down as it accomplished the turning needed to avoid the obstacle and then to recover. And you can see at the very end of the curves, then the robot is, it's kind of started out with the left to right motion. And then after going around the obstacle, it gets back to the left-right motion in a straight line, at that, along the same line as what it started with. So here's a different type of robot. Here we have a humanoid type of robot, and it's doing something very challenging, which is walking up a set of steps, but these steps are a bit irregular as well. So it's a matter of not only achieving some kind of motion, but doing so while keeping the overall system balanced, and not falling forwards or backwards or to either side. So then that's a matter of having some logic to do the balancing, using the arms as well as the motion and the legs are all possible things to be done. Although we can see here that, the arms are not playing a big role in the balancing, so it's just the direct control of the legs. But, if one wanted to add balancing motions of the arms, that's certainly also a possibility. Here's another different type of robot, which is this exoskeleton. And so this, robot is working in conjunction with the person and applying different forces and motions. And so then this is, a product that different audiences are interested in. And it's, basically the exoskeleton is able to add strength to what the person can do. But, here we're saying it's also can be used in training the person to do exercises properly and things like that. So very complex control. This is a student project here. So here we have, the physical robot, the simulation of the robot, and then these two robots are being led by a person who's going through a set of positions, set of postures, and then the robots are following along. So now we're adding in the motion tracking as part of the control system, and the inputs coming into the controller is to do some motion tracking and then apply that both to the virtual robot as well as the physical robot. So the virtual robot can then be used again to check out behavior of the system before the physical prototype is built. So here we have a pick and place robot. So it's taking the peg from one location and putting it in another location. So the particular robot model on this slide has all rigid bodies, and it's able to, perform the function. We see some wobbling of the pin when it's set down, and that's just a factor of the contacts between the end effector and the pin, being released as the end effector releases the pin, and then the pin also makes contact with the, basically the object is being set on. And so then we get this irregular behavior. But because of the rigid bodies, the robot arm itself is moving in a very prescribed way. So then here's the same robot, but now we have added in a flexibility into the lower arm here. And so we can see the stresses being developed. And then, depending upon the stiffness of the component that's made flexible, then that can introduce some vibration because now we have the flexible degrees of freedom to allow the vibration to occur. And so then this becomes extremely useful to be able to use the virtual prototype to check out any possible vibrational issues. And then, as the motion, the flexible motion and the vibration influences the exact position of the end effector, one may need to check out if the positioning is within specification. And if it's the positioning is not within specification, then what needs to be done is one needs to either change the controller to reduce accelerations and anything that might excite the vibration, or maybe the controller needs to be changed so that it comes to the target position and actually waits for the system to settle down a bit before the pin is released. But in this fashion, one can use the virtual prototype in order to check out these possible issues and resolve them before the physical prototype is built. So as a little experiment, then we took the same robot as before. It's going through a different sequence of positions. But it started out with the end effector. The end effector had a mass of 6 kilograms. And so the experiment here was to greatly increase the end effector weight to represent it holding on to a substantial mass. So the mass was increased from 6 kilograms to 60 kilograms, and then went through a series of positions. And there's 6 curves here, and they're representing the X, Y, and Z location of the end effector. The top curves, let's see, how do I want to explain this? So if we look at the very beginning, we have a blue and a green curve that start out at the top at time 0. And then, so the robot's going through a set of motions. So you can see that the position is very consistent for both of them until, a couple things are happening. One is that the robot arm is going through some kind of accelerations. The other thing is the robot, and we'll see this on the next slide, by the way. The robot is stretching out, and so then as the distance to the side increases, then the load on the flexible component increases, and so therefore the effect of the flexibility becomes more noticeable. And then when there's an acceleration, as we see here, now we're starting to see the vibration. Basically, the blue curve is showing the heavier mass, and so we can see this variation, and also see with the blue being a heavier mass, it depends on the excitation, but we're kind of seeing some lower frequency to the vibration because of the heavier mass, but that's not a huge effect. But we do see the amplitude of the vibration being much higher with the heavier mass, which is what we would expect. And then the next two curves are the basically the orange and red curves, and same type of thing. Everything's consistent until we get to the point of the arm stretching out, and then we see the higher amplitude with the heavier load. And then the bottom curve, blue and yellow, again, we're seeing the higher amplitude motions here, but also at a bit of a lower frequency. And all that makes total sense. And so now we'll look at the arm going through its motion. So then here's where it's stretching out. Here's where the stresses get higher on the flexible component. And, this is a bit of an extreme case, but I wanted to make it extreme so it'd be easier to see just at a glance. So, I mean, this probably with the amplitude of the displacement here of the flexible body, it probably wouldn't last very long. Well, depending on the material, I suppose. But so, the point is not to say that there's going to be this much deflection in the flexible component. That's probably going to be quite rare, but I just wanted to make it easier to see. But you can imagine that even with much less deflection, still at the end effector, it'll be significant. So, and if we were to look at the output data, we would be able to correlate high stresses with high accelerations, also high stresses as the robot arm extends out and basically has a longer lever arm, whatever, for the weight to apply stress and forces back to that lower arm. So one cannot go in and change gravity in real life, but one can change the controller to reduce acceleration as needed in the positions where the stresses are starting to get high and so forth. So this kind of feedback is really helpful to then figure out at what point of the work cycle does there need to be a change to the controller to reduce acceleration. This one is now we're applying the flexibility to the gripper fingers, and then we're also applying flexibility with the bottle that's being picked up, and so the first one here we have the flexible fingers and the rigid bottle, and then we have both flexible fingers and flexible bottle. So RecurDyn's capability to model the different components is both linear or modal flex bodies as well as nonlinear flex bodies is really important. I think the nonlinear flex body modeling is really helpful when there's contacts between the different components because all the degrees of freedom are retained in the flexible component, and that's used to figure out the local stiffnesses very accurately for the contact modeling. Whether you have sliding or rolling contact, basically you're going through a lot of different local positions, and so you want to be able to have a complete set of data to represent that properly. Okay, and then again, we're seeing a study looking at stresses on the object being picked up. And in this case, the fingers are rigid, but this is a way to look at what kind of loads are being applied to the product being worked on. And, there may be specifications on limits on those forces. And so as the motion occurs, the question is the force high enough to prevent the slip with the object being lifted up, but not so high that it's causing damage to the object? And when one is, let's say, using a robot and an assembly line, and maybe the items being handled are some kind of product in a package, there can often be important limits on how much of a load can be applied to the packaging. So this last one here is in a very interesting area, which is that of a medical robot. So this particular product is able to use different tools during the surgery. And so there's a notion of changing from one tool to the next. And a lot of surgical devices are like this one with long, slender components. And so then, the ability to look at those components as being flexible bodies, and to be able to look at, how they respond to different excitations as they're being used, that can be really important. Okay, so to summarize here, we've been talking about having a simulation capability with multiphysics to be able to properly represent the behavior of all these different types of robots. And we have a table here that kind of goes through, with starting out with, basic simulation of a robot, and then adding more and more sophistication. So for many years, for decades, people have used rigid body kinematics to be able to move a robot through different positions, and to be able to relate the different input motions to the overall positioning of all the components in the robot. So that's a pretty fundamental capability, and I think there are many products out in the marketplace that could do such simulations. And then the next step is to add dynamics into the system. Now we have the option of applying torque inputs to drive the robot. Also be able to get reaction torques, use that for motor sizing. And then, tracking, really focusing on tracking forces in the simulation, being able to calculate energy usage when we look at the force times the displacement, and also power with force times velocity. And then also with dynamics, having contacts determine some of the motions and behaviors and so forth. So that would start out as being contacts between rigid bodies. And then the other thing that you could have with dynamics is the option for flexibility within a joint. Having flexibility in the joint can add certain fidelity to the model, but it doesn't really capture flexibility of the components, because with the flexibility of the components, then you have, even though it's small motion, you have some motion of the component, relative from one end to the other and so forth with the flexing, which then can have some effects on momentum and so forth, which then affects the behaviors and vibrations and so forth. Okay, the next one, next level of sophistication is to add in a controller. Now you can have, closed loop system where you're pulling in sensor data and making, basically real-time adjustments on what the system is doing in order to meet certain target goals. It's also possible to have an open loop controller and just do a prescribed set of operations and so forth. And all these things are adding a lot of capability to looking at what the robot can do. And then now we start adding flexibility, so we can add a modal flex body, which is linear flexibility, and that enables us to look at basic deformation, vibration type questions. Once you get your results, you can run the results through a FFT in order to get outputs in the frequency domain, and that could be quite useful. Understanding what's happening in the frequency domain can be quite helpful in the controller design. And then the last thing I'm listing here is to add a nonlinear flex body. So as mentioned earlier, the nonlinear flex body enables accurate descriptions, simulation of flexible contacts between flexible bodies. And also the notion of the mass distribution, can be helpful. Especially if you happen to have a robot where it has some components that are flexing with larger displacements, maybe some kind of a ribbon or something as part of the system, then the nonlinear flex body can handle those very large deformations. So hopefully the takeaway from this presentation is that there's different levels of robotic simulation, but RecurDyn has the different modules needed to do all these different levels of simulation, and especially the ability of RecurDyn to embed a nonlinear flex body within the motion model, the assembly of the robot. That's a great capability. It's not generally available, and the fact that it's all integrated into RecurDyn makes it very efficient then to include these flex bodies, whether they're mobile flex bodies or nonlinear flex bodies. They're easy to add to the model, and we have a capability to basically toggle between the rigid body and mobile flex body and the nonlinear flex body. And that becomes very, very powerful in assessing these systems and basically using the right type of flexibility in different stages of the design process according to what is being studied. So that is the end of the presentation.